Awesome. So we are live. Hey everyone, this is Siwei from DoraHacks. I think Aryan, could you please just mute for a sec because there's some. Thank you, Aryan. I'll keep doing the intro. Thank you all for joining us today for the demo session of the DoraHacks Space Resources and Exploration Grant. Today, we're really excited to have team NMITSat joining us to present a demo for their project CANSAT, a new grantee project in our grant program, and previously received CDR clearance for CANSAT India 2023 organized by InSpace. So congratulations to the team. I'm really excited about today's demo session. And for everyone who's tuning in, if you are also into space and satellites, I'm pretty sure you will have some great takeaways. Before we kickstart the session, let me just give you a quick introduction about who we are and what we've been working on to foster space innovation. So DoraHacks is a leading global hackathon organizer and developer incentive platform. We love to support innovation in blockchain, quantum computing, space tech, and many other frontier tech fields. To date, we have supported 8 early-stage projects working in the space sector with our ongoing long-term space resources and exploration grant. So everyone building within the sector is welcome to participate and receive support from us. And actually, more excitingly, last month, we launched another bigger initiative to foster space innovation, which is our Starship Use Cases Hackathon with 100,000 US dollars in prizes, considering the vast potential of space exploration offered by Starship's lift capacity. We have developed 18 use cases and 2 open challenges for hackers to tackle. Use cases include orbital hotel, space farming, routers for global Internet of Things, metals from the moon, etc. 2 open challenges: a novel satellite constellations and recreation facilities for space hotels. Through this hackathon, we like to motivate all space enthusiasts with engineering skills to build their solutions for space. So feel free to click the links below in the description. There you will find more details about our grant and hackathon programs. The submission portal is open, so join us now, and we can't wait to review all your submissions and provide support for your projects. Lastly, for the audience, during the demo session, please feel free to share any questions you have in the YouTube chat room. I'll make sure to ask the team your questions at the end. Now, without further ado, I'm excited to pass the mic to the team. So welcome. Thanks so much for joining. Why don't you start by introducing a bit about yourself, about the team, what you guys have been working on, etc., before jumping into the demo. Feel free to kickstart.
Sure. I'll take over. So myself, Aryan. So I actually handle the flight software, sensor, and the ground station at the team NMITSat. Hemant here has actually solely been actually responsible for building the mechanical gyroscope. So our mechanical gyroscope is actually a unique kind of gyroscope. So generally, for any gyroscope, we actually require 2 gimbals, but in our gyroscope, we just require 1, and we'll just show later on how it actually operates. Shubhadeep here is responsible for all the structure parts, so he has been really helpful from the beginning to the end on designing and printing out the structure that we have. Uh, Regarding the overview of what CANSAT is, I'll just share my screen so that will actually make it more clear.
Sure, go ahead.
Yeah, I hope my screen is visible. Yeah, cool.
Yeah.
So, CANSAT is just a small satellite. So, as the name uh, tells itself, CANSAT. It's a CAN-sized satellite. So we have a cylindrical tube. So the height of the tube is actually 30 centimeter. So the whole height of this tube is 30 centimeter, and we have two parachute. We have first parachute and the second parachute. We got some objectives from the ISRO side, and those were like the speed of the CANSAT should be like 20 meter per second, and after a height of like 500 meter, it should get reduced to 5 meter per second. So it's like that. So that's why we have a dual parachute system. So whenever the CANSAT will actually deploy, then the first parachute will actually open and the speed will be 20 meter per second. And as soon as we reach a height of 500 meters, then our second parachute gets open. So due to that, the speed actually get reduced to 3 to 4 meter per second. Then we have electronic section, the gyro section, and the EPS. So I'll just, yeah, so it's like that. So it's the outer structure. So as I told, the total height is 30 centimeter, and it is divided as such. I can, yeah, I'll, I'll just skip over to the mission objective because the rest part is pretty theoretical, so audience may get bored. Yeah, yeah. So it's like that. So we have a sounding rocket. So with the help of that sounding rocket, our CANSAT will go up to a height of 900 meters to 1 kilometer, and after that, it will get deployed. At this specific height, the speed of the CANSAT will be 20 meter per second, and after it has reached, as I told, 500 meter, a secondary parachute is deployed. So first, one cube parachute is deployed. So with the help of this cube parachute, we are able to achieve a speed of 20 meter per second. And as soon as we reach 500 meter, a secondary parachute is deployed, which reduces the speed from 20 meter per second to 3 to 4 meter per second. Now, the now we have the gyroscope. So the main purpose of the gyroscope is to make our CANSAT stable, because our CANSAT will be traveling from a height of 900 to 1 kilometer to the ground. So there may be many external disturbances that will be involved. So that's where our gyroscope actually comes into play. I'll just show you a rough structure of the gyroscope, and Hemant will be happy to take over to explain more about how it works. Yeah. So, Hemant, can you just unmute yourself and tell how it works? Hemant, you are mute. We can't hear you.
Hello.
Yeah.
Yeah. Okay. So from here, I will be explaining about the mechanical gyroscope that we have used. Basically, for any satellite or any space object, when you talk about its stability, we go with the two options. First ones are the reaction wheels, and second one are the control moment gyroscopes. In case of reaction wheels, we have like three wheels which are arranged in a perpendicular order of all the according to each three of them, and they create reaction on the basis of their angular momentum. That is how a reaction wheel works. In case of a control moment gyroscope, we use two wheels, but as we have guidelines, according to the guidelines, we have some weight constraint in our CANSAT. So we have come up with a new idea, which I call as mono-gimbal attitude stabilizer (MGAS). So in this, what we use is we use a single flywheel, that is single gimbal, and it you can understand its working just if you understand the precision, you'll get to know about how it works. Like for for first two axis, you can just imagine how a normal gyroscope toy works. If and can you show the next page, and I can explain. Next. Yeah. So basically, when if a disk is rotating, and we can imagine the angular momentum in a direction perpendicular to it, and if we apply a force in a direction perpendicular to it, we get reactive torque in a perpendicular plane. So if we had some video, I could have explained you better. So using the same mechanism, we can stabilize any body in two axes. But in this case, we have used two servo motors. First motor will rotate the gimbal in a single plane, and the second servo will rotate everything like whole setup in a 90-degree plane. But I'll show you in the CANSAT how we have incorporated it.
Yeah.
Okay. So as we can see, yeah, this is our gyroscope, and this is the flywheel that we have used here. So this flywheel, when this servo rotates this flywheel in a direction like this, we get a stability in this direction. And to get the stability in other direction, the whole setup moves like this. So we get the stability in all three axes. Basically, I can explain you with the help of a reaction wheel. Yeah. So as you can see, this is a normal reaction wheel that we have used in our first satellite, which is a StudSat 1 in 2007. So all these motors you can see, these motors are the slot for the flywheels or the gimbals you can say. So we have one, two, three, and one fourth here. So in this, we use four flywheels. So the weight of this thing comes approximately to be around 2.2 kgs. But we have the weight constraint here of 700 grams. We have to design whole of our satellite in 700 grams. So according to these guidelines, we have come up with this new novel idea in which we'll be using only a single flywheel, and by playing with the direction of the angular momentum, we can reorient the whole satellite. So this is how our gyroscope is working, and also I would like to share a little bit of the transmission that is happening. Just a minute.
Hemant, I
Yeah.
think so. You're
Yeah.
on.
Okay,
Yeah.
got it. Okay, so this is our EPS subsystem, electronic system, and in this we have incorporated many sensors. The first one is this one, which is a BME 688 sensor. Its main purpose is to sense the pressure, and accordingly, it will give the altitude of the satellite. And the main thing that this sensor can do, it can sense the type of gas present at that altitude. So this is one of the bonus objectives that our satellite gives, in addition to the guidelines that we have according to ISRO. And other we have used the main OBC as the TNC 4.1 board, uh, which has like many advantages over other boards like Arduino or other boards. It gives more than 5 to 6 RxTX pins, so we can connect at a time more than 4 to 5 UART devices. At the same time, it supports more than 3 I2C devices, so that is one of the advantages. And for the location, instead of GPS, we have gone with the Quectel L89 module. Quectel L89 module works on the Navic system, and which is a Indian based navigation system. So, and for the transmission, we have used simple XB modules, XB-S2C Pro. And as you can see, this is currently in a working stage. Transmission happens through this rubber duck antenna, and it is received using uh, this this XB receiver module, which is simply connected to a CPU, you can say. and we have made our own ground station, which has been designed by Aryan. And you can see here all the readings we are getting, like accelerometer data, gyro data, pressure, temperature, altitude, speed, and other data like the orientation and all. We are planning to add, and we can store these data inside a SD card, which is being put in the TNC module. So yeah, this is the brief about how our satellite is working.
Cool. Thanks, Hemant. I can just add on a bit more to that because like he explained majority of the stuff. So to make things more clear, because the satellite was already integrated. So we have a TNZ 4.1. So that is our OBC. By OBC I mean our onboard computer. Then we have an SD card, a camera, a Quectel L89. So Quectel L89, as Hemant told, is the GPS sensor. Then we have BME 680. So this is actually a 4-in-1 sensor. So this sensor gives us the reading for pressure, altitude, temperature, humidity, and we have a BNO 055. BNO 055 is actually used for the orientation of the gyroscope. So it tells on how much angle our gyroscope is actually, our CANSAT is actually deviated. So yeah, and then I can show you a bit of the flight software on how it looks. So here is just a rough state diagram on how our flight software actually operates. So we have a start, and let's just jump to here. So whenever our satellite gets on, we send a command from the ground station, that is TX on. So the satellite will actually start transmitting the data, and then uh, if the altitude is less than 700 meters, then it starts transmitting and it reads the data from the sensor. As I told, we have a BNO 055. BNO 055 will give us the reading data required for the gyroscope. We have a separate flight software for the gyroscope, but if the altitude is like less than equal to 600 meter, then after a delay of 5 seconds, we just rotate a servo. This servo is actually responsible for opening the second parachute that we had. So if I just go to the decent control system, yeah. So it's like this. So we have a pin type servo here. I'll just zoom in to make it more clear. Just a second. Yeah. Yeah. So here we have a pin type system, and this is actually attached to a servo. And when it rotates, so the upper lid actually comes out, and a second parachute comes out. So this is what happens when our CANSAT actually will reach a height of 600 meter, and we have like took a delay of like 5 seconds because we actually want to shoot it exactly at a height of 500 meter, and it should not throw any error as such. So yeah, I'll just go back to the flight software. Yeah. So that's why we are having a dot right 90, and all the data that is there, so that is actually saved to a card and then is transmitted to the ground station. Here we have the gyroscope system. So all the readings are actually taken by BNO 055. Then using some formulas, we actually calculate the pitch, roll, and yaw that are required to orientate back the satellite. And these pitch, roll, and yaw are actually provided to our gyroscope, and accordingly our gyroscope rotates. And due to the reaction of that, our NMITSat reorientates to the original position. So this is how a CANSAT actually tries to stabilize itself. Yeah. Yeah. So that was actually a overview of what we are trying to do and on and where we are right now.
Thank you, team, for the great demo. Not only sharing with us the deck you prepared, and also showing us the physical device, which is really great. So thank you so much. Let me just quickly browse if we received any questions from the live audience.
Cool.
Okay. While we wait for the live audience questions, I will just raise a couple of questions from my end. Firstly, I'm interested in knowing, like, what is the hardest part in this project, CANSAT? What is the biggest challenge that you guys faced, and how did you overcome it?
Sure. So I'll take that. So when we actually started the project, then we actually thought like the project is simple because when we actually made all the slides and all, then we were like, we will be able to easily do it. But when you actually start building the stuff out and start integrating things, then the real problems arises. So the first problem that we faced was actually in the gyroscope because this is a new type of gyroscope and we had no reference that we could actually take up. So we actually took help from various faculty members and various scientists from ISRO itself. And still we are doing some calibration and all. But yeah, so making such kind of gyroscope and making it a bit perfect and working is first thing that we actually face. Second was the communication problem. So in any device that is there that is up in the space, we actually can't go up in the space and fix it. It's not really feasible. So that's why the communication should be strong and working. So while we were using some external modules, we still face some issues on that end to fix the frequencies and make our own ground station antenna. So these were two major problems that we had. And one of the advice that we actually got from our faculty, and that we can actually say it like so our faculty member has worked with ISRO for a long period of time, for like 2 decades or so. So one of the advice that he gave was like, you have to make your satellite so that you are prepared for it to fail. So then you will actually get to know what all you should do is so that your satellite should not fail. So he actually guided us well, and like it happened like if we went to him with solution, so he actually first took out three problems that were in the solution. Uh, then we actually worked on those problems, and following a curve like this, we were actually able to make it uh, close to non-failure, because at last we can't 100% say that it will not fail surely, but we can like just try to make it more stable version. Yeah.
Sounds awesome. Thank you so much, Aryan, for sharing with us. You guys have done a great job, and hopefully, because I actually have a follow-up question, because I know you guys plan to purchase a 3D printer. That's how you plan to use the grants, and I'm wondering what is your plan, like what is your roadmap gonna look like in the next half year or in the next year? If you could share a bit more on that, that is going to be appreciated.
Sure. I'll again take it. So right now we have a structure, but like as you can see, our outer body is still not ready. So earlier we had a 3D printer in our college itself, but that was actually not much useful to us, because it took like a time period of 3 to 4 days to actually print out something. So due to that, our speed on that end was a bit slow. So the 3D printer that we will actually get will actually help a lot to iterate faster, because uh, one thing that I personally believe is like ship fast, I trade faster. So we want to like keep on experiment with the outer structure and all. So that is the roadmap for the next 1 to 2 months, I would say, because the launch is now actually scheduled in Jan to Feb. So we'll actually make sure to ship the whole satellite by December mid at max. Then regarding the team NMITSat as whole, so team NMITSat, the sat part actually depicts a satellite, but we are like more than that. So we are also planning to take part in a Mars rover competition that is again happening next year by and that is conducted by ISRO. So after having this launch, we'll focusing on making a rover. Yeah. So yeah, that's the roadmap.
Awesome.
Thought roadmap. Yeah.
Yeah, awesome. Thank you so much. I hope the grant is helpful for you guys to build your project faster, and hopefully everything goes well in the next couple of months. I'm looking forward to more good news from you guys. Yeah, I can see that we haven't received the questions from live audience, but we do receive some heart emojis. So I think it's a good time for us to wrap up. Before we wrap up, I just want to highlight again that the submission portal for our Starship use cases hackathon is already open. We have prepared a prize pool of 100,000 US dollars and thoughtfully designed 18 use cases and 2 open challenges for you to tackle. We also have our space resources and exploration grant program in place to support space innovators for the long term. So we welcome everyone who has a passion for space to join us and shape the future of space exploration. If you want to learn more about us and our initiatives, feel free to click the links below in the description to our grant and hackathon pages. In the description, you can also find a link to CANSAT. There you can find more details about CANSAT as well. So with that being said, I want to say thank you again to the team for this wonderful demo. Really appreciate your time. And thank you to all the audience for tuning in today. We do have more space-related live sessions prepared for you. So make sure to follow us on YouTube and on Twitter at DoraHacks so you won't miss out on any of our upcoming live sessions or any updates about our initiatives. We will see you soon. Have a good one.
Thanks a
Yeah.
lot. Yeah, thank
Thanks a
you.
lot.